Okay, now we should have sound too. Lorenzo, I think we'll take like hour and a half. I want to be done by 8:30. If you are there, please introduce yourself. I see Xander. I see Lorenzo. Who else is here? The sound is bad? There's an echo. Are the people having an echo situation? Xander says it sounds fine. Stefan, how about you? How's the sound? Anyone else having sound issues? Lorenzo says he's having sound issues. Stefan says the sound sounds okay. Lorenzo, I think it might be on your end. Cool. It's 7:04. I'm going to give people one more minute, and then we'll get started at 7:05. Yeah, two tabs open will definitely, that's a good strategy for making it echo, for sure. Cool. So 7:05, there's 7 or so of us. Please introduce yourself if you just joined us in the chat. I'm going to go through the chapter test from chapter 5, exponential and logarithmic functions, which is on page 348 of your textbook. I'm just going to start from the top and go to the end. There's 23 problems. I think it'll probably take me about an hour, hour and a half. If at any point you have any questions that you need me to clarify in more depth, please stop me by asking a question in the chat, and I'll hopefully improve my ideas or my explanations. I'm going to start with number 1. If it gets towards the end and there's any of the word problems that you're at the end of the chapter test that you want me to go over, or there's any previous quizzes or tasks that we did in class that you want me to go over, please let me know. Oh, and Shiva says I should state whether things are core or extended, which is a great idea. So this is function composition. So this was core from last unit. So this won't even be on our quiz for real, except for verifying things are inverses by composition is an extended standard on this unit test. Cool. That's a great idea, Shiva. I will do that. I will make sure I label things as being either extended standards or relating to extended standards or relating to core standards. Okay. So here we go. I've got f of x equals x plus 2 over x minus 2 and g of x equals 2x plus 5. In A, I'm supposed to find f composed with g. So f composed with g is another way of saying f of g of x. So I'm taking my f of x function, and wherever I see an x, I will put a g of x. So f of x is blank plus 2 over blank minus 2. And now I'm going to include my g of x function wherever there was an x. 2x plus 5, 2x plus 5. And let's simplify. So this equals 2x plus 7 over 2x plus 3. Okay. I can see that the g of x function was defined over all the real numbers. And I can see that this function is going to have a limited domain. So when it said state its domain, I need to find the domain of this function. Lorenzo is asking me that you do not have a page of notes for unit tests. That is correct. You do get a page of notes for a midterm exam, for a final exam. You don't get a page of notes for the unit tests. Anytime we have more than one unit on the same test, you get a page of notes. Anytime it's just one idea, like one unit test, you do not get a page of notes. So here, I want to find the domain of this function. I found f composed with g. This is f composed with g of x. And now the domain. Well, I know I'm not allowed to divide by 0. So the value here, if x was 1.5, then 2 times 1.5 would make 3. So if x was negative 1.5, then 2 times negative 1.5 would make negative 3, plus 3 would be 0. Division by 0 is not allowed. X cannot be negative 1.5. So the domain is the set of x values such that x does not equal negative 3 over 2, or 1.5. Another way of writing that same idea would be to say negative infinity to negative 3 over 2 in union with negative 3 over 2 to infinity. Cool. All of that is part A. Part B. Find g of f of negative 2. Okay, so I haven't yet found the g of f function. So that's going to be my first step. And I'm going to find it with negative 2 as the input. So the g of x function is 2 times something plus 5. And that something is going to be the f of x. So 2 times x plus 2 over x minus 2 plus 5. And I'm supposed to plug in negative 2 for x. So 2 times negative 2 plus 2 over negative 2 minus 2 plus 5, which is just 2 times 0 plus 5, which is 5. So that's B. All of that was A. And now C is I'm going to plug negative 2 into my f of g of x function, which I already found. Oh, Xander's off. That was quick. Bye. So part C, plug in negative 2 to the f of g of x function. So f composed with g of x is equal to 2x plus 7 over 2x plus 3. And then f composed with g of negative 2 should be 2 times negative 2 plus 7 over 2 times negative 2 plus 3, which is negative 4 plus 7 over negative 4 plus 3, which is 3 over negative 1, so negative 3. Cool. Any questions on number 1 from the chapter test on Unit 5 from page 348 of the textbook? Seeing no questions, I'll move on. Determine whether the function is one-to-one. Ooh, now I kind of need to pull up the standards. Do we have any standards about one-to-one functions? I think we have standards about functions being invertible. So this relates to an extended standard. So A, I'm thinking about y equals 4x squared plus 3. I'm going to sketch a quick graph. I would probably just do this in my head. If I was on a test, I'd be like, oh, it's a skinny parabola that has a y-intercept at 3. And then I'm able to check in my head, okay, this function is going to have two inputs that both give the same outputs. So this is not one-to-one. Because two inputs here and here give the same output. So, no. Lorenzo, you want to tell Stefan about whether or not we get a page of notes? Since I just answered that question when Lorenzo asked it. And oh, Shiva's asking, yes, you do get to use Desmos for the extended standards, not for the core standards. B. Root x plus 3 minus 5. Well, that's another easy one to sketch a graph of. So I'm thinking about in my head, okay, that's a square root graph that's been moved left 3 and down 5. So something like this. Oh, I'll do it in a different color. And yes, that's 1-to-1. It is always increasing. So I can go back here and say, yes. In this function, every input has exactly one output, and every output has exactly one input. Stefan, no problem. Thank you, Shiva and Lorenzo. Agreed. We do not get notes on a unit test. We only get notes when we're taking a test on more than one unit. So that would be like a midterm exam or a final exam. That's when we get a page of notes. That's it for number 2. That one is not one-to-one. That one is one-to-one. Questions on number 2? Okay. Seeing no questions, I'll move on. Find the inverse and check your answer. So this is definitely extended standard, and it's definitely on your test. Can I work on a problem from the stuff we learned this week? So Stefan, we learned this week about logistic functions and about curve fitting. And both of those are extended standards. Neither of those is core. And this chapter test doesn't have anything about either of those concepts from this week. But will you remind me, Stefan? And I'll go do one of the problems from the previous sections to practice for what we did this week. I think there's some in the chapter review, but there aren't any in the chapter test. So, Stefan, remind me around 8 to look at something from this week. Sound good? Okay, so here I'm writing the inverse of f of x equals 2 over 3x minus 5, and then I'm going to check my answer using function composition. So in order to find the inverse of a function, oh, shoot. I said this was extended, but it's really both. So this part, finding inverses, is core, and checking your answer is extended. So finding the inverse first. I've got f of x equals 2 over 3x minus 5. I'm going to rewrite it in terms of an input variable and an output variable. So a equals 2 over 3b minus 5. Right now, a is solved as a function of b. I want it so b is solved as a function of a. So I'm going to start by cross multiplying. A times 3b minus 5 equals 2. So 3ab minus 5a equals 2. Add 5a. So 3ab equals 2 plus 5a. And divide by 3a. So cancel, cancel. B equals 2 plus 5a over 3a. So the inverse function, f inverse of x, equals 2 plus 5x over 3x. So that part was all core. Now I need to check my answer. Check your answer. And this is going to be extended. So I've got f of x equals 2 over 3x minus 5. And I've got f inverse of x equals 2 plus 5x over 3x. Okay, and to check your answer, I'm going to use function composition. So I'm going to show that f of f inverse of x is equal to x. And I'm also going to show that f inverse of f of x is equal to x. So f of f inverse is 2 over 3 times 2 plus 5x over 3x minus 5. And that gives me 2 over, let's see, these 3's can cancel. 2 plus 5x over x minus 5, which I'm going to need to make a common denominator. So 2 plus 5, 2 over 2 plus 5x over x minus 5x over x. So 2 over, let's see, 5x minus 5x now cancel. And I've got 2 over x, which is 2 times x over 2, which is x. Hurrah! Okay, so I just showed that f composed with f inverse of x is equal to x. And now I have to show that f inverse of f of x is equal to x. So f inverse of f of x is 2 plus 5 times 2 over 3x minus 5 times 2 over 5. Okay, so that's 2 plus 10 over 3x minus 5 over 6 over 3x minus 5. Now I need a common denominator on top, which is going to be 2 times 3x minus 5 over 3x minus 5 plus 10 over 3x minus 5 all over 6 over 3x minus 5. Whew. So I've now got 6x minus 10 plus 10 over 3x minus 5 all over 6 over 3x minus 5. Okay, it's looking good. So 10 and 10 can cancel. So 6x over 3x minus 5, invert and multiply, times 3x minus 5 over 6. Cancel, 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 gives me just x. Okay, so there it is. I checked my answer by showing that f of f inverse of x was equal to x, and f inverse of f of x was equal to x. So that whole process is an extended standard. Okay? State the domain and the range of f inverse. So for f of x equal to 2 over 3x minus 5, the domain is, well, let's see, I can't divide by 0. So let's see, 3, I'm going to have, well, if this was 5/3, then 5/3 times 3 would be 5, and 5 minus 5 would be 0. So domain is the set of values x such that x does not equal 5/3. And the range is, well, is there anything I can't get out of this function? Well, I don't think this function can ever equal just 2. No, it could equal just 2 if this down here was 1. This function cannot equal 0 is what this function can equal. Because if I divide by a massively large value, I'm going to get a really close to 0, but never actually 0. So here, y such that y does not equal 0. And then for f inverse of x equal to 2 plus 5x over 3x. The domain, and this is nice because it allows me to check my work up here. Hopefully, if I found the range of f of x correctly, it'll be the domain of f inverse. Is it true that this function has a restricted domain so that x does not equal 0? Yes. If I made x 0 here, then 3 times 0 would be 0. I would have division by 0. That's not allowed. So looks like I got the range correct up there. And here it's x such that x does not equal 0. And the range must be the domain of f, which is the set of values y such that y does not equal 5/3. Let's see, that's because if I had like a billion here, I would have 2 plus 5 billion over 3 billion, which would be really close to 5/3, but this would never actually equal 5/3. Yeah, so Shiva, that was what I was getting at. The other way of finding the range for a function is to invert it and find the domain of the inverse. So when I was here, that was hard to see. But now that I'm looking here, oh, it's really easy to see that the domain of this function is the x value that makes x can't be 0 because I would have division by 0. So as soon as I know the domain of f inverse, I can go back and fill that in for the range of f. Does that answer your question, Shiva? Beautiful. Great question. Okay. Any other questions on number 3? Cool, Lindy. Okay, number 4. If the point 3, -5 is on the graph of a 1-to-1 function f, what point must be on the graph of f inverse? Hopefully that's a really easy one. -5, 3. Inverse functions have the inverse inputs and the inverse outputs. The inputs and outputs have been switched. So if this was an input and this was an output, then f inverse must have the point -5, 3, where -5 has become an input and 3 has become an output. Any questions on number 4? Hardest one yet. The extended test has how many questions? I know there are 3 core standards, and there are 8 questions total. So the extended test has 5 questions. Shiva. Solve each equation algebraically on 5 through 7. Here we go. Number 5. 3 to the x equals 243. So I know that 243 is the same as 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So 3 to the x equals 3 to the 5th. Looks like x equals 5. And of course, I could check it with a calculator by saying that what is x equals log base 3 of 243, and it would tell me that x equals 5. To check. Cool. It's number 5. Out of the way. Number 6. Log base b of 16 equals 2, which means that b squared must equal 16. So square root, I've got b equals 4. You might say -4. Certainly, -4 squared is 16. But generally, we restrict the base of a log to positive real numbers. We don't generally allow negative bases to our logs. So there we are. Log base 5 of x equals 4. So let's see. That means that here, I'm on number 7. Let's move 6 a little smaller. Number 7. Log base 5 of x equals 4, so that 5 to the 4th equals x. Well, that's 5 times 5 is 25 times 5 is 125 times 620. Okay, so 625. 625 equals x. There we go. 5, 6, and 7. Any questions on 5, 6, or 7? Oh, and I'm supposed to be saying, so let's see. Graphs of inverse function. I would probably say this is a core concept. Being able to find inverse functions and knowing what that means. And then back here, using logs. So this is core again. So core. Forgot. We have a core standard on using exponents and logarithms to solve problems. Use a calculator to evaluate each expression. Okay. Just so you can see my work, I'm going to use Desmos. Of course, while you're on the core standards test, you will not have access to Desmos. On the extended standards test, you will have access to Desmos. So, but you could do this hopefully just as well on a scientific calculator. Make sure you know how to do this on a scientific calculator. E to the 3rd plus 2. It looks like number 8 is 22.09. 3 decimal places. 22.086. Number 9, log of 20. And of course, that's the common log base 10. So log base 10 of 20 is 1.301. Number 10, log base 3 of 21. If you want a scientific calculator and not like a TI-84, you'd need to use the change of base formula. So you need to say that's log 20 over log 3. I, of course, have a log base, so I can say log base 3 of 21. Whoops, 21. 21. But let me just show you that that's the same as if I was on a scientific calculator, log 21 over log 3. Either way, you're going to get 2.771. And number 11, the natural log of 133. 133 is 4.89. Oh. Okay. 11, 10, 9, 8. I would say you're unlikely to get anything that easy on your test, but that is a core standard to be able to use exponents and logs. Cool. Number 12 and 13. Okay, so looks like I need to do some graphing. I'd prefer to pull up some graph paper. So let's see. I think I have some graph paper, or let's just look some up. Link graph. That'll work. Great. Okay. Use a given function to find the domain graph. Okay, so I'm going to be doing 2, so let me copy that. Okay, so this is going to be number 12. F of x equals 4 to the x plus 1 minus 2. Find the domain. So on number 12, A, find the domain. The domain of any exponential function is always all reals. X such that x is an element of the reals. Okay, and B, graph F. Okay, so I can see, it looks like I'm going to have a horizontal asymptote at -2. That's going to be my asymptote. Asymptote. So I'm going to let my graph go down there. Okay. So I'm on B. Let's go ahead and make an XY table just because it's a good habit to be in. I'm going to choose -1 at the middle, and then -2 and -3 and -4 and 0, 1, 2, 3. So Negative 4 plus 1 is negative 3. 4 to the negative third power is 1/64 minus 2. So that's 1 and 63/64. Then here, negative 3 plus 1 is negative 2. So that's 1 over 4 squared, which is 1/16, minus 2 is 1 and 15/16. Negative 2 plus 1 is negative 1. So I've got 4 1/4 minus 2 is, oh, this should be negative, negative, negative 1 3/4. Negative 1 plus 1 is 0. 4 to the 0 is 1. 1 minus 2 is negative 1. 0 plus 1 is 1. 4 to the first power is 4. 4 minus 2 is 2. 1 plus 1 is 2. 4 squared is 16. Minus 2 is 14. I think I'm already going to be off the graph at 14, so I won't do 2 or 3. Great. So I'm going to sketch in my horizontal asymptote down here at negative 2. Oh, and by the way, graphing core and exponential function, graphing logarithmic and exponential functions is a core standard. Okay. And then I think I'm going to graph in blue today. So I had negative, oh, let's give a scale. This is negative 1, 1, 2, 3, 4, 5, 6, 7, 9, 10. Negative 1, negative 2, negative 3, negative 4, 5. 1, 2, 3, 4, 5. So I've got negative 4 gives me 1 and 63/64. Very close to negative 2. And still very close to negative 2. And now it's only 3/4, getting closer. Negative 1, 2, and 14 is already off the graph. So I'm seeing that my curve looks something like that. Okay, there is f of x equal to 4 to the x plus 1 minus 2. Determine the range in any asymptotes. See, the range is the set of values y such that y is greater than negative 2. The asymptote is clearly at y equals negative 2. D. Find f inverse, the inverse of f. Okay, so the inverse of f, well, I need to say, let's switch into an input variable and an output variable. So a equals 4 to the b plus 1 minus 2, and solve for b. A plus 2 equals 4 to the b plus 1 log b plus 1 equals log base 4 of a plus 2. Just trying to keep it all on one slide. Let's see. That means b equals log base 4 of a plus 2 minus 1. Okay. And very clearly, the range, as I'm supposed to show in step E, the range is greater than -2, because this inverse function can't have inputs that are less than -2, because the domain of a log function is always restricted to positive values. So I'm just going to agree that that is the range. We found it correctly in step C. So here I found the inverse function, which helped me to see the range, as we talked about a couple problems ago. Log base 4 of x plus 2 minus 1. And graph the inverse function. So to graph the inverse function, going back to my graph, I'm going to graph the inverse in green. And I just need to switch the inputs and the outputs. So now I'm going to say -1 and 63/64 gives me -4, which is down there. 3, -4. And -1 and 15/16 gives me -3, which would be right there. And -1 and 3/4 gives -2, right there. And -1, -1. Oh, looks like I moved those points over. So here we go. That's better. Okay, -1, -1, 2, 0. And 14, 1 is already off my graph. So there we are. That is the graph of f inverse of x equal to log, whoopsie, log base 4 of x plus 2 minus 1 in green. And it has a red asymptote at x equals -2. Beautiful. Okay, in the interest of space, I think I'm going to say move over. So copy, give ourselves a new slide, paste, and oops. Get down. Okay, let's go back and grab our graph from this page. Here we go. Okie doke. So number 13. We're still looking at a core standard. 13. Find the domain of f. Well, here I've got f of x equal to 1 minus log base 5 of x minus 2. And, well, the domain is, I know that a log function can't have values that are less than 0 in the argument, or 0. So x here must be greater than 2. So part A, the domain is the set of values x such that x is greater than 2. Okay. B, graph f. Again, I'd like to make an xy table, but this time, because I'm looking at a log function, I think you'll remember from when we talked about graphing logarithmic functions that it's much easier to find the inverse, the exponential function, then get an xy table for the exponential function, and then go back and plot the logarithmic function. So we're going to do things a little bit out of order, and we're going to go ahead and find the inverse right now. So in order to do step B, I'm going to do step D. 1 if A equals 1 minus log base 5 of x minus 2. Oh, and I wanted an input variable and an output variable, so b minus 2. That means that a minus 1 equals the opposite of log base 5 of b minus 2. So that means 1 minus a equals log base 5 of b minus 2, which means b minus 2 equals 5 to the 1 minus a, which means b equals 5 to the 1 minus a plus 2. So the inverse function, f inverse of x, is equal to the 5 to the 1 minus a plus 2. So I'm going to use that now to choose values in my xy table. So I'm still going to be graphing f. So I'm going to pick y values that I would plug in here and get the corresponding x values in this function. So let's see. I'd like to center around 1. So I'll use 0 and -1 and 2, and then 2 and 3 and 4. So -2. 1 minus -2 is 3. 5 cubed is 125, plus 2 is 127. 1 minus -1 is 2. 5 squared is 25, plus 2 is 27. 0, 5, let's see, 1 minus 0 is 1. 5 to the first power is 5, plus 2 is 7. 1 minus 1 is 0. 5 to the 0 is 1, plus 2 is 3. 1 minus 2 is -1. 5 to the -1 is 1/5, plus 2 is 2 and 1/5. 1 minus 3 is -2. 5 to the -2 is 1/25, plus 2 is 2 and 1/25. And, of course, 2 and 1 125th. Okie dokie. Let's give ourselves y-axis and x-axis. Nope, I have to go down a little more. So let's put it there. Will be better. And that way I can get, oh, I can't really get 27 -1 in there anyway. But I can get 7, 0, I think. 1, 2, 3, 4, 5, 6, 7, 0. So I'm going to be graphing this function in red. So 7, 0, 3, 1. 2 1/5 gave 2. So 2 1/5, 2. 2 1/25 is 3. And 2 1/25 was 4. So I've got a function that's got that vertical asymptote at 2 and is going to be going off that way. Okay, so that's f of x equals 1 minus log base 5 of x minus 2. You are welcome, Stefan. Sorry I had to leave early. Oh, and Stefan wanted to go over stuff from this week, but he didn't remind me about it. Oh well. Okay, so what have I done so far? Check, check. Determine the range and any asymptotes. So let's say I did A and I did B. And can I squeeze C in here? I think I can. C, the range is the set of values y such that, let's say, the range of any log function is always all real numbers. So y is an element of the reals. And it does have an asymptote. It has a vertical asymptote at x equals 2. And I forgot to put a scale, did I? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 9, 10. 1, 5, -1, -2. Okay. Okay, so check. I already found f inverse. Looking here, the domain of this exponential function is clearly all real numbers. So yes, this was the correct range for f of x. Check. And let's graph f inverse, which I'm going to do in blue. So -2, 127, well, that doesn't quite fit. -127 is up pretty high. 0, 7 we can fit. 0, 7. 1, 2, 0, 7. 1, 3. 2, 2 1/5. 3, 2 1/25. 4, 2 1. There we go. Okay, so we got a function that's coming down like so. Okay, putting those asymptotes in. I have one horizontal asymptote on the red function, on the blue function there, and a vertical asymptote on the red function there. Of course, these inverse functions are reflections of each other across that line, y equals x. Okay, check. Any questions on 12 or 13? Seeing none, I will move on to solving some equations. How nice and easy. Okay, 14. 5 to the x plus 2 equals 125. So that means log, well, let's just solve it this way. 5 to the x plus 2 equals 5 cubed, because 125 is 5 cubed. So x plus 2 equals 3. So x equals 1. 14. 15. Log of x plus 9 equals 2. So that means 10 squared equals x plus 9. So 100 equals x plus 9. So x equals 100 minus 9 is 91. That was 14 and 15. (16) 8 minus 2e to the negative x equals 4. So minus 8 minus 8, negative 2e to the negative x equals negative 4. Dividing by negative 2, e to the negative x equals 2. So rewriting as a log, negative x equals the natural log of 2. So x equals negative ln of 2, which I could then approximate with a scientific calculator. Negative ln 2, negative 0.69. And again, this is a core standard using exponentials and logarithms to solve problems. 17 log of x squared plus 3 equals log of x plus 6, which means that log of x squared plus 3 minus log of x plus 6 equals 0, which means, let's see, the difference of the logs is equal to log of the quotients. So log of x squared plus 3 over x plus 6 equals 0, which means that 10 to the 0 equals x squared plus 3 over x plus 6, which means that 1 equals x squared plus 3 over x plus 6, which means x plus 6 equals x squared plus 3. Whew, okay, which means 0 equals x squared minus x minus 3. Ooh, is that going to factor? Let's see. X minus x minus 3. Does not look like it factors. Dang. So that means I need the quadratic formula. you will not have any problems that require the quadratic formula on your exam. So A equals 1, B equals -1, C equals -3, X equals -b plus or minus the square root of b squared minus 4ac all over 2a. X equals -1 is 1 plus or minus the square root of -1 squared is 1 minus 4 times a is 1 times c is -3 all over 2 times 1. So x equals 1 plus or minus the square root of 1 plus 12 is 13 over 2. Now that's all good. Are there actually two solutions? 1 minus root 13 over 2. Well, now I need to approximate that, because if that's less than 6, it's not a real solution. So 1 minus square root of 13. Looks like we're all good, though. It's not going to be less than 2. Negative 1.3 plus 6, that would be positive. That, if I plug that in there, that'll also be positive. So those are both real solutions. That's my answer. And really, I'd actually prefer this answer to the approximate answer, but they're both okay. Okay. How do we do? That was kind of a lot. Any questions on 16 or 17? That's a great question, Lindy. So Lindy's asking, how come I had to check that both solutions worked? And how did I check? Which are both excellent and powerful questions. Not something we've really talked about, so not something that's actually going to show up on your test, because it's not something we've discussed. But it is entirely possible that you can arrive at solutions that are extraneous solutions, solutions that you think are the answer because your process yielded them as an answer, but aren't actually solutions to the equation. So if, let's say I'd gotten here -7. So -7 might have made sense here, and it would have been a solution to the quadratic. And -7 could go in and be -7 squared is 49 plus 3. That'd be okay. But -7 could not go in here. -7 plus 6 would be -1, and you can't have the log of a negative. It's outside of the domain of the log function. Log arguments have to be greater than 0. So it's impossible to have log of -1. That's not a real answer. But it is an answer we might have arrived at down here. So I need to check, was 1 minus root 13 over 2, was that greater than -6? Because if it had been less than -6, then when I plugged it into this log argument, it would have given me a non-real answer. It would have been impossible. So we need to check, because in solving a log equation, it's possible to come out in answers that aren't real answers. And the way that we check is we plug them back into the real solution and say, are those real answers? If when we plug in an answer to the original equation, it's an error, a domain error, then we should probably not have it be a solution. But none of that is on your test tomorrow. But it's a great question. Totally a real thing. Okay. 18. 7 to the x plus 3 equals e to the x. So if 7 to the x plus 3 equals e to the x, let's see. Well, I'd like to get 7 to the x plus 3 equals e to the x. Well, let's try using a log. So log base 7 of e to the x equals x plus 3. So that means x times log base 7 of e equals x plus 3. And x times log base 7 of e minus x would equal 3. So x times log base 7 of e minus 1 would equal 3. So x must be equal to 3 over log base 7 of e minus 1, which is something I can plug into my calculator. 3 over log base 7 of e minus 1. Negative 6.17. X is approximately negative 6.172. Okay, that was 18. 18 and 19. Log base 2 of x minus 4 plus log base 2 of x plus 4 equals 3. And I know that the sum of two logs is the log of the products. So log base 2 of x minus 4 x plus 4 equals 3, which is log base 2 of x squared minus 4, and that equals 3. And that means that x squared minus 4 must equal 2 to the third. So x squared minus 4 equals 8, and x squared therefore equals 12. So x equals, and here's another situation where I should check for both plus or minus root 12, but, root 12 Root 12 minus 4 is still going to be negative. So neither of these are real solutions. So here's a situation where when I plug this in up here, they both make a negative in the argument of the log, and there is no solution. I can't plug either of those in. So let's check that work. Now, in the core standards test, you will not have Desmos, but I want to make sure I'm showing you things right. So let's make sure I haven't made a mistake. Base 2 of x minus 4. Ew. Yeah, tomorrow would be better if you don't mind. Is that all right? All right, thanks. Sorry about that. Good night. Sorry for the interruption. We're avoiding vacuuming. Let's see, I was at log base 2 of x minus 4 plus log base 2 of x plus 4. And that should equal 3. Looks like it equals 3 at 5. So where did I make my mistake? Yeah. 4.899. X minus 4, x plus 4. The sum of the logs. Minus 4x plus 4. Ah, it's 4 times 4 is 16. There's the problem. 16. So 16. So when I add 16 to both sides, there we go. Now I'm at 16 plus 8 is 24, and there will be a solution. My fault. Glad we checked. Okay, so 16, so that is 24, and x equals the square root of 24, which I just checked on Desmos, is about 4.899. Okay, but notice that x cannot be, so x is not negative. So even though negative 4.899 squared would be 24, x cannot be, x does not equal negative 4.899. Because if I were to plug a negative value in to this logarithm, I would get a negative argument of the logarithm, which is not allowed. Whew. So again, there's a situation where, as we refer to Lindy's question from back here on 18, I might have said x could be plus or minus 24 to start with, but no, x cannot be the negative root of 24. It must be the positive root of 24. No, none of these types of problems will be on the core test tomorrow. You will not have any quadratics that come up. Like this one came up into a quadratic, that one came into a quadratic. None of your log problems will result in quadratics. So you won't have to worry about extraneous solutions like these. That's not something we covered in class. Cuckoo. Okay. 20 is fast. Let's do 20. So 20 is a quick one. and 20 is an extended standard. So extended properties of logs is an extended standard. So log base 2 of 4x cubed over x squared minus 3x minus 18. Well, I can start with the log of a quotient is the difference of the logs. So log of 4x cubed is equal to, and then minus log base 2 of x squared minus 3x minus 18. Okay? And then here I can say the log of a product is the sum of the logs. So log base 2 of 4 plus log base 2 of x cubed minus log base 2. Let's see, can I factor that? I think that factors to x minus 6, x plus 3. Okay, 4 is 2 squared, so this is 2 log base 2 of 2 plus 3 log base 2 of x minus the sum of log base 2 of x minus 6 plus log base 2 of x plus 3, which is 2 log base 2 of 2 plus 3 log base 2 of x minus log base 2 of x minus 6 minus log base 2 of x plus 3. Showing all steps, because when I distribute the negative to here and here, that becomes negative. Okay, that was 20. Questions on 20? 21, and maybe I'll try to squeeze in 23. So 21 is not so bad. 22, I skipped the money section. I'm sure you could figure those ones out, but they won't be on the test. So let's not spend our time on it. No one's making 5% interest in a savings account anyway. It's not a particularly good problem. A 50 milligram sample of a radioactive substance decays to 34 milligrams after 30 days. How long will it take for there to be 2 milligrams remaining? So I know that in general, A of T is equal to some initial amount, A naught times E to the KT. That'll be my formula for all of these radioactive decay problems. And here, a 50 milligram sample decays to 34 milligrams. So started with 50, got to 34, E after 30 days. So 34 fiftieths equals E to the 30K. So 30K equals the natural log of 34 fiftieths. So K equals the natural log of 34 fiftieths all over 30. So pulling up a scientific calculator. K equals the natural log of 34 50ths all over 30, negative 0.0129. Okay, how long will it take for there to be 2 milligrams remaining? So putting all of this off to the side, if I now know that A of t equals A naught E, okay, and A naught, I know A naught. A naught is 50 E to the negative 0.0129 t. I'm going to solve for t such that there is 2 milligrams remaining. So when will 2 equal 50 e to the negative 0.0129 t? So 2 50ths equals e to the negative 0.0129 t. So negative 0.0129 t equals the natural log of 2 50ths, and t equals the natural log of 2 50ths all over negative 0.0129. So time t equal to the natural log of 2 50ths over negative 0.0129, which is the value I saved as k. T equals 250.39 days. All right. That is about my time limit. We did an hour and a half. Good, solid work. Should we do 23 real quick? As I said, there will not be any money problems on the real test. So 22, though I'm sure you could figure out, is not the best use of your time as far as practice problems go. 10 log of the ratio of the songs, I is the intensity of the sound, and I naught is 10 to the negative 12th watt per square meter. The shout of a single person measures 80 decibels. How loud will the sound be if two people shout at the same time? If the intensity is doubled. So the shout of a single person, so I know 80 decibels equals 10 log of I over I naught. So that means the intensity, let's see, 80 decibels equals 10 log of some intensity shouting over I naught 10 to the negative 12th. So that means 8 equals log I over 10 to the negative 12th. So that means 10 to the 8th equals I over 10 to the negative 12th, which means I equals 10 to the 8th times 10 to the negative 12th, which means I equals 10 to the negative 4. So that's the intensity of one person shouting. How loud will the sound be if two people shout? So 2I equals 2 times 10 to the negative 4. So now I'm going to go back and find the decibels. Decibels equals 10 log of our new intensity, 2 times 10 to the negative 4, over I naught, 10 to the negative 12th. So pulling up a graphing calculator or a scientific calculator, 10 log 2 times 10 to the negative 4 over 10 to the negative 12. 83 decibels. So if 2 people shout, decibels equals 83 decibels. So 2 people shouting doesn't sound that much louder as 1 person shouting. So only 83 decibels compared to 80 decibels. The pain threshold for sound is 125 decibels. We need 74,400 people. How many people in the crowd need to shout at the same time for the resulting sound level to meet or exceed the pain threshold, ignoring any possible sound dampening? So we want to know how many people need to be shouting. So we want to get to 125 decibels. That's the pain threshold, equals 10 log of, I'm going to call the number of people shouting N people times 10 to the negative 4th. That's the intensity of 1 person shouting over I naught 10 to the negative 12th. So 1.25, no, sorry, 12.5 dividing by 10. I can do that. 12.5 equals log of N, the number of people shouting, times the intensity of 1 person shouting, 10 to the negative 4th, over 10 to the negative 12th. So that means 10 to the 12.5 equals N. Let's see, can we divide 10 to the negative 4th by 10 to the negative 12th? That's going to be 10 to the, let's see, when you divide by, you add the exponents, so minus 4 minus negative 12, it's going to be 10 to the 8th. Because negative 4 plus 12 is 8. So N equals 10 to the 12.5 over 10 to the 8th. So 10 to the 12.5 over 10 to the 8th. Looks like 31,623 people need to be shouting to exceed the pain threshold. 31,622.78. So 31,623 people must shout to exceed the ears pain threshold. And see, I suppose that would probably, if something like it, might come under extended because we're applying some properties of logs to solve questions. So I'll call it extended. It's also kind of core, but you wouldn't see a problem that hard on the core standards. That one, that's core. Cool. I'm going to go ahead and save all of these image files to Google Drive. And you've got this video, which you can go back and rewatch if you need to. I know I went a little fast there, Dan, because I wanted to get it all in. And that's it. All there is. Any last questions before I go? Okay. I'll see you all tomorrow. Good luck on the Unit 6 exam tomorrow.